I hope you calculated the signed area, or rather approximated the signed area of the function g of x on the closed interval from 1 to 5 using 4 rectangles, and utilizing the right, the left, and the midpoint rule. If you haven't done so, make sure you try this on your own. At this point, I'm going to show you how this is done. I will do this algebraically and show you using Desmos after I've done it algebraically. So we are going to focus on the algebra from here on out and not so much the graphical thing. Although it is intimately connected to the graph, we are going to calculate using the algebraic techniques that we saw earlier. Now, because we are on the interval from 1 to 5 and we want to use 4 rectangles, the width of each rectangle is going to be the same. So the width of each rectangle has to be what we get when we take the distance from 5 to 1 and divide by 4. When you look at that, that means the width of each rectangle needs to be 1 unit. Because I am dealing with starting at 1 and ending at 5, that means my subintervals are going to be the following. The first subinterval is going to go from 1 to 2. The second subinterval is going to go from 2 to 3. The third subinterval is going to go from 3 to 4. And the fourth subinterval goes from 4 to 5. That's going to be each of these subintervals that determines each individual rectangle. So the individual rectangles are going to be, one of them is going to be from 1 to 2, the other is going to be from 2 to 3, another is going to be from 3 to 4, and another is going to be from 4 to 5. If I want to use 4 rectangles, no matter what area I am calculating, no matter which rule, it's always going to be the length of rectangle 1 times the width of rectangle 1 plus the length of rectangle 2 times the width of rectangle 2 plus the length of rectangle 3 times the width of rectangle 3 plus the length of rectangle 4 times the width of rectangle 4. We're going to add up 4 rectangles. Let's do these 4 rectangles using the right-hand rule. The right-hand rule would say the length of each of these rectangles is determined by the right-hand value of each subinterval. In the first rectangle, we use the first subinterval. So we're going to say g of 2 is going to determine the length or height of that rectangle. The width is going to be 1. From 1 to 2 is width 1. Plus, let's go to the second rectangle. Length of the second rectangle is g of 3 using the right-hand rule. The width is 1. The third rectangle. The third rectangle uses 4 for the right-hand rule. So g of 4 is going to be the length times a width of 1. And the fourth rectangle is going to use 5 as the right-hand value. So g of 5 is the height of that rectangle. The width of that rectangle is 1. Now I simply calculate g of 2, g of 3, g of 4, g of 5, plug it in, multiply each one by 1, add them up, and we get the total area. Okay, if we do this, g of 2 plugged into x squared plus 2, 2 squared plus 2 gives me 6. So I get 6 multiplied times 1. G of 3 gives me 11. So 11 times 1. G of 4 gives me 18. So I'd have 18 times 1. And G of 5 is going to be 27. So I end up with 27 times 1. That means the area is what you get when you add those 4 rectangle areas up. If you do that, you get 62. So the approximate area using the right-hand rule is 62. Let's go ahead and look at the left-hand rule now. The left-hand rule would say, instead of utilizing the right-hand values, we're going to use the left-hand values for all of our rectangles. It's a lot easier to copy and paste, so I'm going to do that. So instead of using 2 as what our input for our first height of our first rectangle, I'm going to input 1. And into our second rectangle, I'm going to input 2. Into our third, the height of the third rectangle is going to be determined by g of 3. The height of our fourth rectangle is going to be determined by g of 4. So we input 1 for our first rectangle, 2 for our second, 3 for our third, and 4 for our fourth. Once again, some of these have already been calculated. Some of these have not. One of these has not. G of 1, it turns out, is 3. G of 2, I already calculated that. That was a 6. G of 3, I already calculated that. That was an 11. And G of 4, I already calculated that. That was an 18. In this case, the left-hand rule gives me an area of 38. So the approximate area using the left-hand rule is 38. Notice that these two are pretty far apart in this scenario. 62, pretty far from 38. In the last scenario, our left-hand rule and our right-hand rule gave us the exact same number, but that is not always the case. In this case, they gave us vastly different numbers. Let's go and calculate the midpoint rule. I should say, let's calculate the approximate area using the midpoint rule. If we go to our first subinterval and we look for the midpoint, should be pretty clear that in our first subinterval, the midpoint is 1.5. In our second subinterval, the midpoint is 2.5. In our third, it's 3.5. And in our fourth, it's 4.5. So the midpoint rule would say 1.5, 2.5, 3.5, and 4.5 are what we need to plug in to get the heights of the rectangles. These I have not plugged in yet, so what we would do is just plug those in. When I said I haven't plugged those in yet, I haven't plugged those in before. If you do plug in 1.5 into your function g, you get 4.25. Plus, when you plug in 2.5, you get 8.25. When you plug in 3.5, you end up with 14.25. And when you plug in 4.5, you end up with 22.25. Each width is 1, so you're multiplying each one of those things by 1 and then adding that up. When I typed that in on my calculator, I ended up with an area of 49 using the midpoint rule. The approximate area using the midpoint rule is 49. Notice again, that's in between 62 and 38, but there's still sort of a gap between, there's a much bigger gap in this question between all of our approximations. So our midpoint rule approximation doesn't give us the same as our left-hand rule and doesn't give us the same as our right-hand rule. Our previous problem, they were all three pretty close. In fact, the left and right-hand rule were exactly equal. And then the midpoint rule gave us something that's pretty close. I want to show you visually why that is happening. If I'm looking for the signed area, I have this g of x graphed. Notice the g of x, as we go out from 1 to 5, does get very large in value. G of 5, remember, was 27. So we get very, very big very quickly. If you're looking for the signed area is the area between the function and the x-axis between 0 and 5 in my case. So this is a pretty big, tall area. I'm going to zoom in just a little bit so we can emphasize all of the functions. So the function here has this blue signed area. If I want to approximate that using the right-hand rule, notice what's going to happen. This first rectangle, we would approximate using where the function value is at 2. So the first, we'd use function value at 2. Obviously, that rectangle is going to be an overestimate of the area under the curve. We do the same thing with 3 on our next interval. Again, this function, we have an overestimate of the area under our curve. My next rectangle, using the right-hand rule, I'd be at 4, again, another overestimate. And then lastly, our last rectangle is going to be g of 5. Again, notice that all 4 of these rectangles are overestimates of the area under the curve in this case. If you used the left-hand rule, that green rectangle would be determined by the height of the function when x is equal to 1. So the green rectangle would change into this. The purple rectangle would be determined by the height of the function at x equals 2. Similarly, the black rectangle is determined by the height of the function at 3. And the red rectangle would be determined by the height of the function at 4. Notice that each one of these rectangles is an underestimate of the actual signed area. That tells us that the actual area should probably be somewhere in between the 38 we got with the left-hand rule and the 62 we got with the right-hand rule. That's just for this problem. Okay, that doesn't always work because as we saw in our last problem, we did left-hand rule and some of those left-hand rule rectangles were overestimates and sometimes they were underestimates. But in this case, left-hand rule, they're all underestimates. So I can say, I know the area is going to be above 38. And when I used the right-hand area, I knew that the area was going to be below 62 because all of those were overestimates. So in this case, we get underestimates with left hand and overestimates with right hand. But we don't always get that in every scenario. If we use the midpoint rule, let's take a look at this. 1.5, 2.5, 3.5, and 4.5. It's hard to see if this is an underestimate or an overestimate, but I will say, you know, for this part of the green rectangle, it's an overestimate, but for this part, it's an underestimate. So it's pretty close. It's not going to be exact, but the midpoint rule in this case is probably going to give us the closest value, I would say, out of the 3 values that we had. Hopefully that makes sense graphically and algebraically. I am not going to force you to do a graph of these things. As you can see, the typing in of these graphs is sometimes pretty difficult to do. But I do want you to, at least in the back of your mind, understand that we're creating these rectangles. And when you add up the areas of the rectangles, you get an approximate value for the area under the curve or the signed area, at least along the interval that we're determining it on.